systems, and they'll be like about 6 or 7 gauges. And our DevOps people will have these dials. And what that dial will be the stock. Will be the stock of the system, because nothing can be done unless you have something in the stock, and then you have to return it. And the future of DevOps will be, initially I think will happen, is because humans don't want to give up control to AI or like that initially, is that we'll all start dialing these things up and down. Because everything is changing a lot. We know we have a systems code deployments are happening, and it's very hard to make memory of anything anymore, because 15 minutes later someone might have deployed something and it's a very different system. So what do you do when you can't have the old way of monitoring where nothing changed in 6 months and everybody knows what the pattern looks like? It's like, oh, I know that pattern, and then as soon as it changes, oh, I know what that means. You don't know that anymore, because you don't know whether it's because of a change, because of the environment, because of the workloads. It's very changeable environment. So I think we have to give up thinking that we're in control, and more, well, at least in control by just observing, and we have to start experimenting. We have to be able to dial up and down in operations and see what happens. The great thing about that is you can see your immediate reaction. You know, you can see the immediate response in your environment. You tweak something, you bring it up, you see if I add capacity, what happens. That improves, but another bottleneck forms. And I think that's the future of DevOps, is learning. Initially, you'll probably have about 12 of these dials, and then someone will come along and say, here's 3 of them that do all the other 12. And eventually someone will say, here's an AI which will do it. And all you have to do is tell the AI, how sensitive do you want to be? What's your risk level? I remember in Interstellar when the guy said, I think, you know, the robot, I forgot his name, but the robot had a level of joke, you know, a level of humor. And I think that's the way for humans. We're good at exploring our limits, moving down and relating to the context. And I think that's where observability is going. We're going to start using observability to control, and the control, when we do things, will impact the observability. We'll have an immediate feedback on the system. We'll see what that does, and we'll learn how the system works. Of course, you want some safeguards, because no one wants to go, let's dial it down to 0 and everything crashes. No one wants that, but there will be, I think we need to do some experimentation on that, because there's no optimal system. Do I have 5 more minutes? Yeah. Okay. Okay. So that's the part where control comes in, observability. Now get back to humans, because, you know, we can't manage systems the way they are today with the data that we're getting in. So how do we go back to building systems that are going to be easier for humans to operate? So we got that control, but still I don't know whether I should intervene. I can tie it to a metric, but I've gone into banks and they are proud of saying they have thousands of metrics, but no one really understands what metric is useful or is a signal. And then they say, well, we'll just apply machine learning to it, and that will figure it out. And everybody say, yeah, that's it. That I can tell you it doesn't. Yeah, and the other initiative is we'll standardize on all the names. Everybody always wants to do that. The problem is we're just naming everything differently. And then we need pattern language. We'll get patterns, we'll put the alerts in. No one does that. The new guy comes in, he's like, okay, I'm going to do it. And he has to have OCD, first of all. You have to have him doing it for a month, and then he burns out, and no one ever, and the next guy comes in, he starts all over again. Oh, I don't like the way he did the patterns. And those patterns are probably not even valid anymore. And it's changing. So I think we have to get rid of looking at logs. Logs, they just go like, "Argh." And that's a signal. And you know what? It's universal. You don't have to send a message and say, this is the timestamp. It was on this server. I want to tell you, these are the 4 parameters I did to it, like the intensity. You know, you see it. It's aggressive. And you infer the state. And what happens when he does it a few times? You think he's mental. The first time it's like, okay, he's a bit angry. The second time, there could be a problem with this guy. Then you realize he's always angry. And what's happened there? We've taken a set of signals and we've inferred a state. We say that this person is an angry person. And that's how humans work. And I think that's how we need to do machines. So my view is microservices or all other systems are going to have to send signals. Emojis, whatever. They have to be something that's different systems. And I think about 15 can cover everything that we need in the distributed world. And those 15 signals map to states. Now, there's no state like on or off. It's like, am I defective? Am I degraded? Like, what happens when you time out? You're degraded. What happens when you fall back to a cache or fall back to something? Yeah, it's degraded, yeah? Defective is when you start erring. So we can take a bunch of all of these signals of how services are working, like they're social, and build up a Twitter sphere from machines. Now, I know that sounds a bit corny, but basically what we need to do is, and how monitoring used to work in the past, and I know I'm overrunning my thing, but the internet has allowed me, is we have to look at humans, take signals, we process them very efficiently, we infer state. We need to do that for microservices. And what's good about that when we start doing that is, instead of asking the service, are you feeling good? Are you operating? We'll ask all of its dependents. Are you talking? So S1 talks to S2, and S2 will tell you how it feels about S2. S1, we need all of the services, a social system where services vote each other out of the containers, out of the pod. So basically they say, I don't think he's operating well. And what the beauty of that is that we can have sensitivity. Because let's say I'm a very resilient system and I can tolerate someone failing. But I might have a colleague that can't tolerate someone. And he has he's critical path or something. There we can define his level of sensitivity to certain signals from another service differently than mine. So then collectively we make a judgment on what the other service is. I could vote, I'm happy with him even though he's failing because I have a fallback or a cache or something, or I'm able to retry a few times. But the other guy might say, I can't retry because I got critical time limits. And for me, he's bad. So, and of course the other guy might be thinking, well, I feel good, I'm servicing everybody. He doesn't know he's even timing out. He might not even know that other people can't connect with him. So the future is going to be looking as a collective system and everybody voting on what is the state of the system. And I think users will also be included in that. And I know we're running out of my time, so I'm going to end very quickly. Just this last slide. Why do we need the signals and the states? It's a small symbolic language. It's compressible. It scales. It will scale across different technologies because it's translatable. It doesn't matter what animal, any animal growls at you, what already you're in trouble. It's universal. So we need a universal language across languages, across frameworks. The signals and the sequencing are ways of easily effective fingerprinting. Fingerprinting of behavior in Windows. The fingerprinting drives us down to the metrics. We still go back to metrics because we still need to understand something. But we use the signals to draw to our attention, to focus on areas, and from the metrics to the traces. Not the other way today is like I just scan anywhere. And then the good thing about that is it's easy to do familiarity, and then also we can forget all of the other stuff, the left and the right. If it's not interesting, let's start forgetting. Humans do that, and it's important to forget because you need to incorporate new information all the time because it is changing every day. Cheers.
We've probably got time for one question, just while you're setting his laptop up. If anyone's got any questions. No questions at all? Okay.
Yeah, I've got one.
Great. We have no microphone. You can shout.
Yeah, I'll shout. You mentioned the sort of participants within the ecosystem and communicating and spotting each other's health. Isn't that what sort of protocols like gossip and things like that already doing?
Yes, yeah.
That's what you meant.
That's it, yeah. We basically, it's a formalization around that. I mean, there are two things that drive something, and if you look at the social environment, the social behavior systems, it's always about status. That's what human mind is designed around. Then there's the sensitivity to certain signals, and then there's also your ability to remember. So because sometimes you forget someone, like you can forget what they did. And that tends to happen, people can forget particular people doing something, and others they don't forget, like, oh, I'm not going to forget what you did. And that's where we have those two levers. So I think we'll create a ecosystem of services, and then all DevOps will be doing is define the sensitivity of your service to another service, to a signal, and then how much do you want to remember that? How long will that carry forward into your future assessment of his state? Oh, one more? Sorry. No, I'll take my mic off. Later. Oh, you want me back on?
I need that.
Oh, you need this mic. Hold on, yeah. Okay. Sorry.
I was just going to ask, thank you for the presentation.
Okay.
Just going to ask about AIOps. What's your opinion on AIOps?
It's very like what we did with AI at the beginning. It's not going to work out at the moment because we really haven't got the model. I remember when Instana started, and we kept saying we have to have AI, and then we hired brilliant data scientists, and they just looked at the model and they kept saying this data is never going to work. Why is it like this? And like because we gave them traces, we gave them metrics, and it's like context. High CPU. Let's take that as give that to a data scientist. High CPU. Can you say that's good or bad? It's very hard. It's contextual. It could be good, or it could be bad. It could be like they're utilizing the system right, or it could also indicate something else. Like if it's low, it could also indicate that you're deviating. So it's very hard to codify those. I mean, you can start to look at patterns over time, and we see phase shifts. But the problem is with the phase shifts is that there's lots of shifts, and we don't know what the root cause of it is. And so for a data scientist, he's going to, when things go wrong, everything goes wrong. But what you see in microservices is, and the problem is the metrics are laggards. They always collected a minute later. So by the time things start to really, become observable, everything is going wrong. Everything looks wrong. So you rarely see that the root cause, even though there's multiple root causes, but it's very hard to extract what was the driver, what were the dynamics. Now, with signals, we think that can be done quicker. We think that those are signals that are, are predictive. They're easy to predict coming forward. When you start doing a retry, what happens, what we see in the microservices is it ripples from left to right. So, okay, take you as a server. So this is me. I'm sorry if I'm going on, but this is me. I evaluate myself over post, get, and put, And then there's another guy here, and he's calling to me, and he has post, put, and get. He's calling into me, and I'm calling into this guy, and he's waiting for me, And he's like, I'm going to kill you, man. But now what happens when he starts acting up? He's going to start flagging. And then on my side, if you evaluate myself, think of me as a grid of 3 columns. How I see myself, how he sees me, and how I see him. Now, when he starts failing, he's going to start failing himself, and then I'm going to start flagging one of my dependents is failing. And what typically happens in microservices, it starts ripping. It's like a domino effect. But those signals are there. We're going to see signals that are more defective signals, degraded signals, before we go into down modes. And I think that I'll see him failing before I fail, and then we'll see the ripple effect. And I think that's easier to see with signals, when there's only 15 signals per service, rather than thousands of metrics that no one really understands. The whole point is that you only ever need to know 15 terms, and those signals map to 4 states. And that's all any DevOps should ever need to do with a microservice. That's the vision. So it's like Esperanto for DevOps.
So it's a very long, quick question.
I'm sure Willie will be around.
Never ask me any questions.
Up next is Yannick from Wealth.
That's the new brief question.
That's me being short. Sorry.
Hi, wow, there's loads of people. I'm Ionuț Crăciunescu from Wealth Wizards. I'm one of the platform engineers. This talk is actually based on the talk that my colleagues Dave Shepard and Pierre Menuet gave at KubeConf U in Barcelona this year, and I'm here because they couldn't make it and they sent me instead. I'm a bit of a mountain bike geek, so you'll see a few more pictures like this, fortunately or unfortunately. Wealth Wizards, it's a fintech based in Leamington Spa. We have 2 applications. One is called Maiva. You can go and register with your email address, give some details. It gives you a financial MOT. Another one is called Churo. It's aimed at financial advisors to help them giving financial advice. Both applications are FCA regulated, and the company is FCA regulated, as in Financial Conduct Authority, is the governing body doing legislation in financial world. So pretty much that everything we do has to comply with loads of regulations. We get loads of auditors from all over the places. Now, our applications, they are microservices based. similar to these bikes in a bike parking lot somewhere in Denmark, I think. There's loads of them. And when we deploy microservices into our production environment, to find a good balance between going fast and be flexible and still comply with change control, for example, we deploy off the master branch. So basically our change control process is, there's a feature branch, development takes place, pull request, classic thing, pull request against master, gets reviewed, gets approved, deploy to master, and that's it. So the pull request in itself, it's our change control mechanism. But since everything goes off master, you can see how that can go wrong sometimes. Wrong as in delayed, similar to these guys waiting to go down the mountain. If everything goes from master branch and you have 3, 4, 5, or 10 changes waiting to go into production, they might all get queued up one behind each other. Or if there's changes coming in, new information, say, okay, this change has to stop. It might delay the others. And we're thinking, okay, how can we solve this problem? It's slowing down our deployment pipeline, it's slowing down developers, we want to go faster. And then we said, okay, what if we make the deployment pipeline large enough so everyone can go at its own speed, have its own path from start to finish, can go as fast or as slow as it has to be, as it needs to be. And we looked at various ways of doing that. Service meshes on one side, feature flags, beta users. Feature flags. If there's loads of changes, let's say you have 20, 30, or 50 changes that they all have to go into your development environment, it becomes a bit tricky to maintain all those changes behind feature flags. There's a lot of overhead. We used it for a while, then we backed out. We found out we spent more time doing pull requests for this change flag, or do this, do that. If A, then B, then C, then E. Oh, okay, I don't want to manage all of that. We still use feature flags for some of the production launches, but it's not the main way we release into production. Similar with beta users and with microservice environments, we've been asked, why not spin up a new environment for every change that I have? And we said, okay, that's going to be insanely costly, difficult to manage, not going to do it. It was an easy choice. And then we said, why not spin up only the changes? I have this change in my microservice A, deploy my change alongside the other ones, and then talk to that change. And here is where Istio comes into scene. Istio in itself, for those which don't know it, it's a service mesh. The way it basically works, it is injecting a sidecar in every pod. That sidecar runs Envoy proxy, and it injects some IP tables rules on the host. And all traffic going in and out of that pod is being redirected and basically goes through Envoy proxy. And there's a bunch of rules in there which tells Envoy how to route traffic, or if it needs to do any traffic controls, if it needs to do TLS, for example. Istio has loads of components. It has a control plane. Citadel is a pod which manages basically PKI for Istio if one chooses to do mutual TLS between pods. It has Mixer. Mixer is responsible with pulling data from Kubernetes API and keeping Istio up to date with whatever is happening on Kubernetes, how many pods, how many services. Pilot is the component which is responsible mainly with creating Envoy configuration and pushing it onto Envoy proxies. So most of the work happens on Pilot, and it's quite CPU intensive. All rules that are pushed from Pilot to Envoy are usable for traffic management. It can route traffic based on headers, in this example, based on user agent. You can do clever stuff with canary deployments. You can tell it even route 10% of the traffic to this set of pods. How did we deploy Istio on our cluster? Basically, is this thing, Istio Ingress Gateway, which is the entry in the service mesh, and the pods themselves, they have Envoy injected. So traffic goes into load balancer, Nginx Ingress controller, goes into Istio Ingress Gateway. That's the entry point into the mesh itself, and then it's all managed by Istio. A bit of a demo time. Hopefully it doesn't blow out in my face. And okay, so this is a dummy example just to show how Istio, how we use it for traffic management. Let's say I'm a developer and I've been told, hey, I don't like this case list over here. I want to change it to something else. I go in my repository, I make a change, I add my new text. In this case, I've already done the change. It's already been pushed. The build time takes a while, a few minutes. And then I can start using it. And I have an extension in my browser. I can go and say, okay, send me a header called xVariantID, which is matching the branch name. I take that one. I go and refresh my UI. And there you go. I can go and see my new changes. And I can use them going forward. If I choose a different number here for a branch which doesn't exist, or if I don't have the header set, it will be routed to the default master deployment, as we call it. So basically the main line. Going back to Istio, the way we do that, we have a deployment tool for Kubernetes that we wrote ourselves even before Helm existed. So for every deployment, we label it with a version matching the branch name. Then we also have a destination rule in Istio. So that's an Istio configuration rule. And the destination rule goes and finds all pods behind this service which have a label ops 1, 2, 3, 4 and makes up a list with them. And then we have a virtual service. Basically, we have two types of virtual services. We have one for the entry in the service mesh and one for traffic within the service mesh itself. And the reason for that is because we want to route traffic based on host name as well. And host name, this is a public FQDN. This FQDN is not available inside the cluster. So you just have to basically do a bit of duplication. And in this rule, the Envoy proxy is looking at headers. If it has the header ops 1, 2, 3, 4, which actually is this example, it will route to a subset of pods that have label attached ops 1, 2, 3, 4. So the traffic goes from Envoy to Envoy directly. It doesn't go through Kubernetes service. It's pod-to-pod communication. This is the virtual service for traffic inside the mesh. It's pretty much similar to the previous one, except it doesn't have this rule, which is matching on the host name. And that's basically it. The only configuration we had to do on Istio itself. Now, how is this managed? We have loads of pods. They all have to be deployed the same. What cookie cutter have we used? We wrote a few automation tools ourselves. One of them is called AutoKube, which listens on the ingress on Kubernetes API for deployments. It has a bit of logic, some templates, and for every pod or namespace, which has an annotation which says Istio enabled, it will go and update virtual rules and destination rules. We do loads of, developers create loads of branches. They live there for maybe 2 weeks, but we don't want the deployments to stay on the Kubernetes cluster for 2 weeks. So that's why we have what we call Kube Housekeeper. It will go and delete all deployments which are older than a timer, 2 days or 3 days, depending on the project. We have discussions with developers and basically we agree on how much time they need them running. And we've also wrote a thing called hpropagate. hpropagate is basically a Node.js module. And its responsibility is to pass headers to downstream systems. It's very easy to use. The only thing we have to do is require hpropagate, and that's it. Now the question is why we've done that. Let's say we have service A calling to service B, calling to service C to doing its workflow. It's nice and easy routing traffic to the first service, service A, based on the headers. But when the outbound traffic goes to service B, no information is there telling me, okay, where should I go? So hpropagate grabs the input headers and passes them to output. By default, it's doing xVariantID. The header I showed it in the previous demo is doing also correlation ID, so you can have a full trace to the system for service A calling B and C and so on. So it's quite easy. Didn't take much time to develop it. It's free on GitHub. The other tools are on GitHub as well, so you can go and use them, have a look. Because we use Istio, we also get Jaeger for request tracing. It's pretty good, to be honest. We get fancy maps. We recently had a request from one of the developers asking, hey, I have this request. Is it going to service X, Y, and Z? I think it does. Let me look on this software called Kiali that comes by default with Istio. And I've got this service and say, yeah, it's all great. 9 months later, so we are 9 months in since using Istio. How is it working for us? Well, it's great. We are pretty happy. We couldn't do without it these days. We'd slowed down so much the deployment and development pipeline. Devs and QA as well would hate us. Probably the business would hate us if we take Istio out. It made releases easier. It also improved collaboration because it exposed developers in QA to a bit of infrastructure, and they have to go every now and then, okay, I need to use this header, is my pod there? So we had more collaboration among ourselves. Was it easy ride? I'd like to say yes. Ish. Istio has a steep learning curve. Kubernetes in itself is complex. Istio is just as complex. There's loads of moving parts, loads of new things that one has to learn. It had some stability issues for anyone using Istios. Yeah, it made that guy fall over, go over the handlebars. Back in the days, I think version 0.5, definitely 0.5, that's when we started using it. 0.6 up to 1.0 snapshot 3. We were getting 503 errors. What was happening when a pod was being terminated or was removed from the cluster, Istio wasn't catching up with that event quick enough and was still routing traffic to that pod. And one way to work around it or to improve it was to add retries at the TCP layer, and that removed most of 503s, but then pilots themselves in default configuration, they were not having enough resources, enough CPU to cope with the workload, so you have to give it more resources. Again, by default, they are deployed using horizontal pod autoscaler. It goes from 2 to 6, if I remember correctly. It goes up and down with the load. We found it's better to have a fixed number of pilots, give them enough CPU to cope with the load, and we are also running it on dedicated nodes on C-type instances, compute optimized. We were at a point where we said, okay, it's quite difficult for us to maintain this thing. We all have Kubernetes, we have Istio, we have loads of issues. Should we still keep it? And thinking about the value it gives us, we said, okay, let's push on, find ways to make it better. And luckily, in time, Istio developers improved CPU usage, and Pilot itself became more performant, and they solved loads of issues. We are now on version 1.2, which we upgraded in January. We didn't have to do any changes since then. It works at rate. We are quite happy with it, to be honest. As a summary, using Istio solved our deployment bottleneck. We were able to deploy every feature individually. We also have plans to use similar traffic management approaches to or release some stuff in production. Something around the UI. It's a bit difficult to explain now. We push the complexity into the platform, so the applications themselves, they don't care what's happening, they are blind. Istio is complex, but it's also feature rich. There's more it can do, so there's more for us to explore. As I said, HPropagate is on GitHub along with the other projects. We also have a medium engineering. By all means, go and have a look. Add comments. This is the end of my talk. Thanks for listening. If you have any questions.
Any questions you want to answer? No questions? Okay, good stuff. Next we've got Alex from StorageOS.
Hello, everyone. Hopefully this will work. Yeah. So I realize that I am the guy standing between you and beer on a warm Tuesday evening in August. And I kind of misjudged the slide deck because I wasn't sure it was 20 minutes, so I kind of put a bit more content in there. So what I'll do is, I'm going to rush through some of the slides, and you can hang around and ask me questions afterwards if you need that. So just a little bit about me. I'm one of the founders of StorageOS. We are building software-defined storage systems that run in orchestrated environments, cloud-native environments. I'm also recently appointed the co-chair of the CNCF Storage SIG. The Storage SIG is a new creation. We used to be called working groups before, but the storage SIGs are now here to help scale the CNCF. So as you're probably aware, the CNCF are the guys behind KubeCon and Kubernetes and a variety of other projects. And we're now over 400 vendors and companies are part of the CNCF, and there are probably about 800 end user organizations too. So the SIGs help the CNCF with some of the work that we're doing in terms of selecting projects and identifying technologies that can help with the different CNCF technologies. So I'd really suggest you have a look at our page there. There's all the minutes of all the previous meetings, and the meetings are public. We often have lots of interesting project presentations in those meetings. So what I want to talk about today is cloud native storage and why this is important. So the obvious thing is there is no such thing as a stateless application, right? So we often talk about containers being stateless and this sort of thing, but at the end of the day, the state has to be stored somewhere. And while we want to have the benefits of containers, and containers make your applications portable, and Kubernetes abstracts away your infrastructure, we need to have a storage solution or storage solutions and technologies that can work in that sort of environment. And what do we mean by cloud native technology? So the first important thing is that cloud native storage is going to be application centric. So today, most storage systems are presenting storage to operating systems or VMs. And what we really need is storage that's being presented to applications and can move around with the applications as the applications move. In a similar way to all the benefits that you've already done to make your applications cloud native and made them portable and able to run on-premise and in the cloud, etc. You also want your storage to be platform agnostic and to have the right abstraction layers in there so that you can consume that storage from different places. Of course, it's really important that storage is declarative. So we go through a lot of effort with things like with orchestrators and Kubernetes to be able to say, this is what makes up my application. I can say it needs these containers with this software, with this network port, with this routing configuration. But you should also be able to say, and I need this type of storage with these type of attributes. And for that to happen, obviously, the storage needs to be API driven. And I put agile, and everybody will roll their eyes because it's cliched. But what I mean by agile there is, in cloud native environments, there are lots of moving parts. It's much more dynamic than a traditional environment. So nodes come and go, you're probably scaling dynamically. And you need to have a storage system that can provide the availability and can provide the performance and can provide the durability and reliability in an environment where everything is changing. And let's not forget that agility also implies things like security, because you typically have multi-tenanted environments. So, in summary, cloud native storage makes your apps better. So what we did, the cloud native storage landscape is huge. There are dozens or hundreds of projects and lots of vendors providing lots of different functionality. So what we decided to do was, we decided to write a white paper that would actually help people to understand what goes into a storage system. And the white paper is fairly long. It covers the things that allow a developer or a DevOps team to be able to figure out what type of storage they need for their application, because we're kind of evolving from sort of an environment where, in the past, an application developer was given storage by an infrastructure team, but now they're actually able to define what their application needs and what type of storage they need. So we define things like the attributes of the storage, the various layers in the storage system, and how they get orchestrated in the management interfaces. It is a 40-page doc. I'm not going to go through all of it. So this is the short version. So inside the storage system, we have a number of different interfaces on how you consume the storage. You have multiple layers of functionality. And effectively, you're choosing a storage system and you're designing a storage system based on a number of attributes. So things like availability and scalability and performance. Because at the end of the day, what you want to do is you want to choose a storage system that's going to match what your application needs. And those attributes can be measured in multiple different vertices, I guess. So things like availability is often thought about, you often think about how do you replicate, for example, and what type of redundancy is the storage. But we also need, because this is cloud native, we also need to figure out things like how you do failovers between nodes, how you move data between nodes. And again, things like scalability often talks about the number of nodes, but you might want to measure scalability in terms of the number of operations that you're doing or the throughput, or indeed the number of clients that can access that system simultaneously. Similarly, performance is measured in, again, different metrics. So we have things like databases or message queues, for example, that might be really latency sensitive. But on the other hand, if you're doing analytics or something like that, maybe the only thing that matters to you is throughput. The other big thing, because in cloud native systems, you kind of have a proliferation of a variety of distributed systems. Those systems, you need to understand what the consistency model for those processes are. So consistency can mean different things to different people, but ultimately it's the difference between the time it takes for something you commit to actually be registered and be readable on other systems. And that is a really important factor, because it does affect some of the other functions, like often you have compromises between availability and performance based on different consistency models, but it can also affect things like durability and your ability to recover, say, from power failures or outages like that. And finally, you also have to keep in mind how you actually deploy and instantiate the storage system. So you have traditional hardware solutions, which obviously are the things that you know and love in standard data centers, but obviously that limits portability. You have software solutions that are extremely portable, and they tend to be more platform agnostic, but they also tend to be based on shared nothing architectures, which give another set of problems or another set of challenges to overcome. And you've also obviously got cloud services. So each cloud provider typically offers 5 to 10, maybe even more different storage services. So how do we access storage? So for the most part, people tend to think of storage in terms of how they access the storage. So you have workloads, and you have an orchestrator that's orchestrating the storage system. But the way that you access the storage is what we call the data access interface. And we did a lot of thinking here. Now, storage can mean the typical things, a file or a storage block device, for example. But actually, more and more in cloud native environments, storage is actually can be anything where you need to persist data, right? So it can be a database, it can be a key value store, it can be an object store too. Now, it's probably fair to say, though, that a lot of the focus and a lot of the maturity in orchestrated workloads has gone into managing volumes. So today, most of the abstractions are how do you get a file system access into your container? How do you get shared file systems access into your container? And while there's a huge plethora of services for object stores and key value stores, etc., most of those things don't have the declarative abstractions to be able to say, I want to start up a new object store, for example, or I want to create a new bucket of space. Now, when we were writing the white paper, we also kind of did a lot of thought to kind of say, what do people actually expect when they think of these different access interfaces? Now, for the longest time, access interfaces used to define the primary criteria for your storage. So if you wanted something that was really low latency, you'd go for block storage. If you wanted something that where you had a shared workload and you had multiple things that needed to access the same files, you'd choose a file system or some sort of shared file system. And if you just had this, huge data lake with lots of information, you'd probably choose an object store. And for the most part, that kind of defines things like your latency and your sharing capability and some of the performance characteristics. So what I'm going to say, though, is that doesn't count anymore, because most storage systems today are formed of a number of different layers. And the different layers can be exposed as any number of data access interfaces. So you have file systems that are built on object stores. And so you have the sharing capability of a file system, for example, but you have the latency attribute, the high latency attribute of an object store, for example. And there are all sorts of really quite complicated layerings. So you can create block stores out of file systems. So Gluster has the capability of doing that. You have Ceph, which is an object store, which also shows up as a file system. So it's kind of so what we kind of said was, okay, so the data access interface isn't how you measure a storage system anymore. It's important. It's one of the things that contributes to the attributes, but it isn't the only thing, because we have a bunch of different layers. And understanding those layers is effectively what you need to understand for your application. So at the very top, you're going to have an orchestrator or your host or an operating system that's doing things like volume managers, or perhaps something like a service mesh like Istio, which is controlling what you access and how you access it. You also have to consider the storage topology. So there are a number of different storage topologies, and this has huge effects on things like availability and performance. So on the one hand, you have centralized storage architectures. So these are typically characterized by hardware that has proprietary interfaces, and they're designed to scale up rather than to scale out. And they're really good at doing low latency, but they're also really expensive because you have to scale them up. You then have distributed systems, which are typically made out of, have software options, or they can be scaled out using commodity hardware. They have much better cost characteristics, and they have much better scaling characteristics. There are a variety of systems, including databases and object stores, that use sharded technologies. There are also things like database projects like Vitess, for example, that use sharding to scale out MySQL databases. And similarly, things like Redis and other things like that. However, obviously, managing sharding has its own complexity, and that's something that needs to be concerned. So each of the different topologies does affect, we already said that it affects things like availability and scalability. I'll leave this up on the screen. We can send this out afterwards, and you can read it in more detail on the website. The other things that affect a lot of the attributes are the data protection. So most applications have some sort of dependency in terms of their architectural patterns that the storage is providing some level of availability. So a lot of the designs on how an application recovers in the event of, say, a node failure or a component failure or a network failure is based on the availability of the data somewhere else, and that implies a dependency on that storage. So at the most basic level, you have things like RAID levels or mirrors, where a storage system is actually just making copies of data or using some sort of parity algorithms to spread the data across a number of disks to allow it to survive disk failures. As one level above that, we have technologies that use erasure coding. So erasure coding is kind of a more advanced form of parity. And this allows you to split the data into multiple little chunks that can be spread around the whole network. And this gives you much higher durability capabilities, because you can now lose multiple nodes, for example, or multiple hard drives. Of course, the calculation overhead of splitting all of those chunks and the cost of sending all of those chunks over the network doesn't mean you have high latency overheads, which means that erasure coding is often found in things like object stores. And then if you want to have distributed reliability, but you can't take the overheads of something like erasure coding, then replicas are typically the answer, where you have copies of the data on more than one node. The storage system will also provide a bunch of data services, so things like replication across data centers, or providing point-in-time copies with snapshots and clones, or indeed securing your data by using some sort of encryption. And of course, we mustn't forget the physical layer, which ultimately does impact a lot of the durability and performance characteristics of the storage system. Pardon me. So we talked about the cloud-native storage needing to be declarative. So what does this actually mean in real life? So the data access interface is that little column C in the picture. So effectively, that's how workloads talk to the data plane in a storage system. But the orchestrator, the Kubernetes, needs to be able to say, I want this type of storage. I need that storage here. It needs to be this size. It needs to have these attributes. So the stuff that you declare, in your pod, in your storage classes. And there are a number of different interfaces that exist. And I'll talk about those in a second. But ultimately, we have two major types. The first type is where a storage system is, natively integrated with an orchestrator. So they will use native interfaces with Kubernetes or some of the CSI drivers, for example. But there's also a variety of frameworks and tools that integrate orchestrated workloads with the actual storage system. So an example of that, and it's also a CNCF project, is Rook, which is actually orchestrating Ceph on the back end, and is kind of taking Ceph, which was sort of designed pre-Kubernetes, and taking those API connectivity from Kubernetes and translating them into the equivalent Ceph functionality. So there's a number of different options on these interfaces. It's probably worth saying that today, most of the focus from all the storage providers and the different container orchestrators is CSI. CSI is the container storage interface, and it's kind of another one of those API standards, like the CRI, the runtime interface, and CNI, the network interface. And this is basically an abstraction layer. So CSI effectively provides a standard API and a standard driver mechanism where Kubernetes can talk to a CSI driver, and that CSI driver has a number of different abstractions that talks to the storage system. So the storage system can now be effectively orchestrator agnostic. All of the standards, CSI is the future, because things like native drivers were becoming extremely unwieldy. So for example, StorageOS was one of the first organizations to build native drivers for Kubernetes. And we actually have our code, our drivers mainlined into the Kubernetes code. But that does mean that every time we need to do a patch, or we discover a bug, or some new functionality needs to be added in, well, you kind of have to upgrade your whole version of Kubernetes. And that is not, that's not practical. So the whole concept of CSI means that we've now kind of got the concept of a driver just like any other driver in any other operating system, and we have that functionality there. So I would strongly recommend that you have a quick look at the SIG storage. We have public meetings every couple of weeks. There's sort of 30-odd vendors there, but there's a lot of independent people and end users there too. And we would really love to have your feedback. So we put a little survey together to kind of figure out what you guys are using most, where your pain points are. And this allows us to help prioritize and focus what we work on next in terms of the projects that we put together or the content that we put together to help. Now, my marketing guys would kick me in the ass if I didn't say a little bit about StorageOS. So I've just got a couple of slides, and I'm going to say this. So StorageOS actually is a cloud-native storage platform. We are actually deployed as a container. We're platform agnostic. We don't have any proprietary dependencies on kernel modules or hardware, which means we can be deployed anywhere you deploy your applications. And we abstract away storage pools out of your clusters and create a simple way to dynamically provision storage using the CSI drivers and providing a rich set of functionality like encryption and replication and compression. Within the Storage OS container, we have both our control plane and our data plane. The control plane provides all of the health endpoints and the availability to understand the state of the cluster and understand the config of the cluster. And the data plane provides all of our virtual storage interfaces, so those data access interfaces we were just talking about, providing transparent failovers, but also things like inline encryption and inline replication and inline compression. And we kind of do this by creating these virtual storage pools that can use any of the underlying storage on any of the nodes in your environment. So it doesn't matter whether you're running this using physical disks on bare metal or virtual disks in VMs or cloud storage like EBS, etc. in your cloud instances. We can just take all of that storage, create a virtual storage pool, and then create your dynamically provisioned volumes out of that. And that's me.
Any questions?
22 minutes, not too bad.
Thank you very much. You mentioned the fact of having compression and encryption related returns. Do you have any metrics that you can give us based on CPU or RAM for unit of storage that this provides? And is that done within a sidecar to the cluster, or you have on your cluster computing to manage the storage?
So it's okay. So there's a few questions there. So Storage OS is actually just deployed as a container. So it's just a single container per node. We're architected to have a very low CPU and memory footprint, so we can easily run with sort of one CPU and a couple of gigs of RAM. Things like we often get questions about things like compression and encryption. So for compression, we've spent a lot of time optimizing that data path, and we use LZ4 as a standard mechanism. And actually, what we've found is that in most environments, you're limited in either IOPS or throughput on the back-end disk, right? So very often, for example, if you're using general purpose EBS volumes, for example, you just have 3,000 IOPS. So actually what we find is that we enable compression by default, because actually that means you're doing less I/O to the disk. But also, more importantly, we also compress the I/Os that are going over the network. So you're actually reducing the network throughput for that replication overhead. And in general, we kind of find that, for example, if your application was bottlenecked at 3,000 IOPS with your EBS volume, you stick Storage OS on top and you get between 6,000 and 10,000 IOPS, because now the compression is basically easing that limit for you. So in general, we see compression speed things up. Encryption, just like everybody else, we have really optimized algos, and we use the AES-NI instructions in the latest, in all the Intel chips from like 2007 or whatever. So, on a 4-core, 500 quid Dell PC, you get 8 gigabytes per second. That's typically way more than your disk can take or your network can take. So that's really not an issue.
Okay, great. You sticking around later, Alex?
Sure.
Yeah, if anyone's got any more questions, grab Alex up. I'm just conscious of pieces of light as well, so we're getting cold. So yeah, big thanks to William, Yoni, and Alex again. If you give them a round of applause for this. The 2nd of October, and as promised, we'll make sure it's a 50th party for a 51st event. And the drinks and bits downstairs. So yeah, thanks for coming. We'll see you next time. Cheers. Cheers, Alex.
Thank you.
Thanks for that. This was really good. Sorry about the duration, otherwise.